Hey everyone, hope you're doing great. So today I wanted to talk about an implementation of Astar algorithm. And in this particular example, what we have is that there is a robot which starts at the red cross position, and the goal is to reach the blue cross by taking the shortest path. The black circles in this figure indicate the obstacles, and as you can see, the A-star algorithm that I implemented gives a path which is of this type. But depending on what heuristic costs and different parameters you use, you might get different paths. And we're going to see an example when this path can actually change its shape. I wanted to actually just run through a few steps of the algorithm that I implemented in Python, and just want to show you that this just goes exactly according to the algorithm that I talked about earlier. So if you haven't checked out my video where I go through an example of how the A-star algorithm works, I definitely recommend checking it out. I'll put up a link in the description and on the top right corner of this video. Let's just get into how the A-star algorithm works. In this particular example, I have defined it in a class format because it really helps in keeping everything in a proper order. So we have an initialization function, which is kind of mainly responsible for defining how the grid is shaped. So if you see in this particular case, we are specifying the minimum and the maximum x and y values which our grid can take, and what's the resolution of the grid. So all those parameters regarding the size of the robot, etc., are specified in this initialization function. Then the next method that we define is the Euclidean distance, which is used for calculating the cost to go from a node n to the goal node. So that's where this is used. And then we directly have a star algorithm. Here, the inputs that it just takes are the start node and end node, and also the obstacles that we have. What we have in this particular algorithm are three data structures. So these are termed as open heap. So open heap is the one which is having elements as tuples. So these tuple elements are consisting of cost and node, as indicated here. The second data structure that I have used is an open dictionary. So the open dictionary has a key value element, and the key here is indicated by the node, and the value is indicated by a cost parent tuple. The third data storing element is the visited dictionary. This thing has node as the key element and the cost parent as the value element. So if you remember the A-star algorithm, when I was describing it through the example, we had that start node, and whenever we used to explore that start node, we used to put a cross on it, and then we started to explore the neighbors. So whenever we cross out an element, we put it inside this visited dictionary, and whenever we are exploring different nodes, we are putting it inside this open dictionary. The next step is to define how the obstacles are laid out. So there's nothing much into this. Then what we have is the initialization step. So this is exactly the same like we talked in the algorithm, where we put in the start node inside this data structure queue. So here we are putting this inside the data structure open heap, as well as in the data structure open dictionary. And this is actually how it's kind of pushed inside the heap data structure. And this is how in Python we define the key value pairing inside this open dictionary. The next thing is to define that if you are at a node n, then what are the nodes that you can explore? And in this particular case, we are having 8 possible directions. So the robot can either move forward, backward, left, right, or in the diagonal direction. So we are having these 8 particular ways, or 8 possible neighbors of exploring. And then we have associated costs with them. So this is kind of necessary because we don't want too many changes in path that we have from a start node to goal node. So what we want is a smooth path, and we don't want the robot to go in the backward direction. Usually we want the robot to just move in a straight or in the forward direction and just take maneuvers left or right till it reaches the goal node. So that's why in this particular example, I have kind of penalized whenever the robot is thinking of going in the backward directions more than when it's trying to go in the forward directions. So now the algorithm just progresses the way it's there in this particular presentation. So we start off with the while loop, and while this open heap is not empty, we keep on repeating it. And the idea is that we choose the first element of this open heap. So this is corresponding to the path P, which has the lowest cost. So the reason I used an open heap is because this is one data structure which automatically sorts all the elements based on the first entry inside this tuple. So that's like the major benefit of using an open heap data structure. And so we automatically have the path B which has the lowest cost. So choosing it becomes really simple. So you just choose the first element, and then the idea is that once this path or this node is chosen, we just define two variables where we are storing the node and the cost. Inside this visited dictionary, we just fill in its entries. So the key value would be the chosen node that we have defined here, and whatever node parent pair is there for this particular node, we just put that inside this visited dictionary. The next thing is that if the head of that particular path P is the goal node, then we return the path P. So in this particular implementation, it works as follows. So once we are sure that the end node is there inside the visited dictionary, we start to find its parent, and then subsequently we keep on doing this until the node we reach is the start node. So the way this algorithm works is that if the head is detected as the end node, then we start to find its parent, and then we try to find that node's parent, and so on and so forth until we reach the start node. So once that's done, we put all of these entries together in this final path list, and then we just return this. So that's how this particular part of the code works. And supposedly, if this doesn't go through, then we just go and explore our neighbors and see which entries or which particular explorations could be used. But before doing that, we remove the path P as indicated by this particular algorithm step, which is corresponding to the lowest cost. Once that's done, we see the 8 corresponding neighbors of that particular node that is removed, and then we calculate what are the costs corresponding to that. So cost to neighbor from start is telling you the cost to come to that particular node end. That's just evaluated using this particular metric. So say you know the chosen cost that's there to come to that path P which you have just removed. So you just subtract the heuristic cost, and the component that you'll have is the G part. So if you remember, the total cost was the sum of G plus H, where G was cost to come to node N, and H was the cost to go from node N to the goal node. So if you want to calculate just cost to come to node N, then we just subtract the heuristic cost from the total cost. So once that's done, then we define these neighbor coordinates. So this is just some additional math that's done. So once these neighbor coordinates are defined, then we start to look whether these neighbors are there in the obstacle or not. So if this exploration is there in the obstacles, then obviously we don't consider it because we don't want our algorithm to give a path which goes through the obstacles. And if the neighbors that are given out are going way outside the grid that we have defined, then that is something also which we don't prefer. So we don't consider those nodes as well. The next thing that we try to do is we calculate the heuristic cost. So for all those neighbors which satisfy this condition, we calculate the heuristic cost, which is using this Euclidean distance method that I just showed on the top. So it takes in input as the neighbor and the end node. Then the idea is to calculate cost to come to this particular neighbor node. So that is 1 plus the cost to come to the node n that we chose when we removed it from this particular heap. Once that's done, we calculate the total cost, which is the sum of the heuristic component cost to come to that particular node and this additional cost. So this thing is kind of responsible for ensuring that we are not going in or preferring paths that are going in the backward direction. We want the robot to kind of steer in the forward direction and try to find a path from the start node to goal node. So with that, we are in like the final stages of this algorithm. And here, what we try to do is that, suppose say the neighbor that you have picked, that neighbor is already there in this open dictionary. So in case the total cost that you computed for this neighbor, you already have a path which is of a lower cost, then there is no point in considering this neighbor. So we reject this. In case this has a lower cost, then we consider this particular node. Another aspect that you want to consider is that it's possible that the node or the neighbor that you are considering to explore, that's already there in the visited dictionary. So if that's the case, then what we see is that if the total cost happens to be greater than the cost that we had of visiting that particular node, then it means that this node is not the one that we should consider, because we already have a visited path which ensures that we have a lower cost of reaching that node. So we kind of skip that up. And if both of these conditions are sort of zero or not satisfied, this means that this is a good node that we can probably explore. So we put this up inside both the open heap as well as the open dictionary data structure, and then we continue. So you can see that the algorithm really progresses in an exactly same fashion as was written here. And with that, we have how the algorithm can be implemented in Python. So now I just want to quickly show how different costs can lead to choosing of different paths. So this is the case where we have the standard costs and we have the standard path. So from the start node to goal node, we go along this diagonal direction, and whenever we hit the obstacles, we kind of go around it. Now, suppose say if I change the cost that's pertaining to going in the forward direction, suppose say I make this 6 instead of 0. So what we expect is that the robot will not go in this direction because this is kind of expensive to go. So what it might do is that it might go diagonally, and then it might go diagonally towards downward side, and then it might go diagonally in this direction. So if I just run this up, what we see is that the path is sort of like more in a zigzag fashion, which is not really good, considering like if you're running an autonomous vehicle or something, then we don't want paths that have so much sort of zigzag movement. In this particular case, you can clearly see that if you start penalizing the case when the robot is trying to move along the x-axis, then it starts to go in those directions which have lower cost, and the path kind of changes. So this is what I actually wanted to point out, is that it's that the path that you have in Astar algorithm, it's kind of really dependent on the costs that you are considering. So it's really sensitive to it. So if you change them slightly, the path that you might get would be quite different. With that, I want to wrap up this video. So thanks for watching it. If you have any questions or comments, feel free to leave them below. Thanks.